X, right? I thought there'd be data. Is anyone out there?
Hello, and welcome back to Mathematical Statistics. I guess I had just stated the delta method last time, and we still need to prove it and then maybe do an example. So we were talking about convergence and distribution, and then the central limit theorem, which gave us some asymptotically normal results, and then the delta method. Okay, so the delta method was originally attributed to a guy named Doob back in, I think it's 1935. And it allows us to take a convergence to a normal through a function. So it goes like this. We're going to let xn be a sequence of random variables such that we already have the square root of n times xn minus theta converging in distribution to a normal with mean 0 and some variance sigma squared. And then we're going to let g be a function that takes reals and spits out reals. And we want this to be, continuously differentiable. We want it to be differentiable and continuous on a neighborhood containing this theta, which is a fixed value. So be differentiable and continuous on a neighborhood around theta. Okay, and we also need that g prime of theta is not 0. And so the punchline was that if we try to look at the asymptotics of putting the x and the theta through this function, that's still going to go to a normal with mean 0, sigma squared, and then g prime of theta squared. So I didn't say that this theta has to be the mean of this guy, but suppose it is. Suppose this theta is the mean of this guy. If you put it through a continuous function like g of x equals x squared, the expected value of this is probably not this, even if you started off that way, with this being an unbiased estimator of this. And yet, in the limit, the expected value of this difference is going to 0 anyway. So this is saying something a little more that we're not talking about formally yet about asymptotically unbiased estimators. But I will define that when we get to it. So let's prove this. The original proof by Doob involved a lot of different Taylor series approximations and lots of little delta x's, which is how it got the, its name, the delta method. I'm going to prove it in what I think is an easier way using the mean value theorem. So recall by the mean value theorem, we can, and for simplicity, I'm just going to take g continuous everywhere. So we can write g of x minus g of theta over x minus theta equals the derivative of g at some theta tilde. And this theta tilde has to be somewhere between the x and the theta. So for some theta tilde between x and theta. Hopefully you've seen that before. Some of you are probably teaching it right now. Okay, so now I'm going to put in the random stuff. And so this is going to become g of xn minus g of theta, theta being a constant, over xn minus theta is equal to g prime of theta tilde for some theta tilde between the xn and theta. Because xn is random, this theta tilde is also going to be random because the xn can move and the theta tilde has to be between xn and theta. So now theta tilde is random because it's just something that we have to be able to find in that interval, and one of the endpoints of the interval is random. So from this, let me just do a little bit of rearranging. I don't know why I just didn't write it this way to begin with. Gxn minus g of theta is equal to g prime of theta tilde times xn minus theta, and we've got all these random quantities in here. And again, theta tilde is a random variable between theta and the random variable xn. Okay, so we were given that the square root of n, xn minus theta, is converging in distribution to a normal 0 sigma squared. And this implies that xn is converging in probability to theta, and this comes from homework 5, number 4. Xn we can write as 1 over the square root of n times the square root of n, xn minus theta plus theta. And if you write it that way and use the fact that this goes in distribution to the normal 0 sigma squared, now apply, I won't finish writing the details, you're almost done, apply Slutsky's theorem, take that 1 over square root of n down to 0, and you will get convergence in distribution to theta. And since theta is a constant, you'll get convergence in probability to theta. So this goes to 0, this goes to theta, use Slutsky's theorem to say something about the whole thing, and then translate it back to convergence in probability, because again, Slutsky's theorem gives you convergence in distribution results. Okay, so continuing on this proof, note that if we look at the absolute value of xn minus theta, that this is strictly greater than the absolute or the magnitude of theta hat minus theta. And this comes from the fact that theta hat is somewhere between theta and xn without the endpoints. Okay, so check this out. We can say something about this theta tilde, which is a random variable. We're going to show right now that it converges in probability to theta. And we're going to get that from convergence in probability of xn to theta. And so if we write, say, the probability that absolute xn minus theta is greater than epsilon, so fix an epsilon greater than 0, this is greater than or equal to the probability that absolute theta tilde minus theta is greater than epsilon, because this guy is smaller than this guy, so this guy has a harder time to be above epsilon, so it will be above epsilon with a smaller probability. And then take the limit on both sides. And so the left side is going to 0 because we already said that xn goes in probability to theta. The limit as n goes to infinity of the probability absolute theta tilde minus theta greater than epsilon. This is less than or equal to the limit as n goes to infinity of the probability of xn minus theta greater than epsilon. And this is 0 since we showed above that xn converges in probability to theta. And so that forces the limit down here to be 0 because it's below 0 and it's a probability between 0 and 1. So we have just shown, by getting that left-hand side limit equaling 0, we have shown that the random variable theta tilde is converging in probability to theta. And there is an implicit an implicit n hidden in there. Theta tilde does depend on n because it depends on x sub n. Okay, so I assumed that g prime, ooh, you know what? I think I stated this wrong. I don't know how I stated it last time. Sorry about the scroll. I actually want it continuously differentiable. And so let me write that down. G prime needs to be continuous. So the way I have stated it here is that G is continuous and G prime exists, but I need G prime to be continuous as well for this to work. Okay, so if that's the case, we're going to scroll, then I can put this convergence in probability through the G prime, and the convergence in probability will be preserved. So there's two things to cite on this. One is we had a theorem that, the only theorem that I really give a special name to was that theorem, and this is not it. So we had a theorem when we first talked about convergence in probability where we said, okay, if xn goes in probability to A and yn goes in probability to B, then we said that xn plus yn goes to A plus B, and we said that xn times yn goes in probability to a times b, and we had a ratio. And the fourth one was we put it through a continuous function. So we had a theorem that says that continuous functions preserve convergence in probability. But if you want something to quote out there in the world, we can also call this the continuous mapping theorem, because that was a theorem stated last time for convergence in distribution, but it actually holds for convergence in probability and a stronger form of convergence called almost sure convergence. So usually the continuous mapping theorem says that if you have a continuous G and you have, well, if you have a continuous G, then xn converging in distribution to x implies that if you run the G through, it still converges. And xn converging in probability to x implies that if you take G of xn, it will converge in probability to G of x. And this other kind of convergence that we don't know about called almost sure convergence will also hold through the function G. So the statement of the continuous mapping theorem usually has all 3 points, in which case you would take this as a result of the continuous mapping theorem. But right now we do have it as number 4 in a theorem that was not labeled or numbered. Okay, so we're almost done. So we have, remember that we had G of xn minus G of theta equaling G prime of theta tilde times xn minus theta. Let me get rid of this stuff over here. So what do I care about? Sorry about the scroll, but I'm going to scroll back up and see what I'm trying to look at. The square root of n times this needs to go to this. So I'm going to take a square root of n on both sides of this. And so I've got the square root of n times g xn minus g of theta is equal to, and I'm going to put the square root of n sort of in the middle here. So g prime theta tilde square root of n xn minus theta. And then we're done, because this guy, by assumption, is going in distribution to a normal 0 sigma squared. And let me just be a little more specific here. It's going in distribution to a random variable x, where x is normal 0 sigma squared. And this g prime of theta tilde is converging in probability to g prime of theta, theta being the fixed constant, theta tilde being a random variable. And so by Slutsky's theorem, the whole left-hand side, I'm sorry, the right-hand side, and then so the left-hand side, goes in distribution to g prime theta times x, which is a constant times a normal, which is again normal. And the expected value of this guy, right, the expected value of a constant times a normal, where x is normal 0, 1, still has mean 0 and has variance. We started with sigma squared, but we'll get sigma squared times g prime of theta squared. So what I was doing there was, if you have x normal 0 sigma squared, a constant times x is normal with still mean 0 and variance sigma squared times c squared. We already know it's still normal, but compute the variance of this and you'll get this. And the left-hand side was the thing we care about. Right? So we're done. So we've got the square root of n, g of xn minus g of theta, converging in distribution to a normal with mean 0 and variance sigma squared times g prime theta squared. Really messy, sorry about that. So we are done. About the rate of convergence here is even harder than talking about the rate of convergence to the central limit theorem, because first you need the rate of convergence given by like the central limit theorem. That gives you the setup. The setup was the square root of n times xn minus theta was converging in distribution to a normal. First, you need to worry about the rate of convergence there, and then you need to worry about how putting it through the g function affects the rate of convergence. And it turns out that this is pretty decent when g is a linear function, but when g is highly nonlinear, this can be pretty bad. Like in terms of if you want to just fix a large n and say, I'm going to treat this thing as approximately normal, it can be bad for highly nonlinear g's. Okay, let's do an example. Suppose we have x1, x2 out through xn. Well, n is going to increase, so an infinite sequence, but they're going to be IID from some distribution with mean mu and variance sigma squared, and this is not a normal. I say that every time because this is so close to looking like this notation, but there's no n, so not normal. Okay, so we know that the square root of n x bar minus mu over sigma is converging in distribution to a normal 0, 1 by the central limit theorem. And so I want to get something that sort of looks like the setup of the problem, which is really just the numerator of this fraction. But this implies if you multiply both sides by sigma, if you multiply a normal 0, 1 by sigma, you still have a normal, and now the variance of that is sigma squared. So this implies that the square root of n, x bar minus mu, is going in distribution to a normal 0 sigma squared. And so I'm just going to look at, I guess I should have given you like what I was trying to solve here. I want to know about convergence in distribution of the square root of n, x bar squared minus mu squared. This is one of the most common transformations used in the delta method. And so what does this go in distribution to? You just realize that this is a delta method with g of x being x squared. So this guy over here is now g of the, so the xn's are now the x bars, which are depending on n, right? So the x bar is some x bar of n. So I'm looking at the sequence of those, not the sequence of the individual x's. Anyway, running this through the delta method, we get a normal with mean 0 and variance sigma squared, and then we're going to take the derivative, and that's 2x, and we're going to evaluate it at the theta, but the theta for this problem is mu, and we're going to square it. So this is g prime of mu squared, which is a normal 0, 2 mu all squared, so it's going to be 4 mu squared sigma squared. And I'm sure I'm sure some of you are wondering why you could possibly even care about what this goes in distribution to. And today we are starting some actual stuff that looks like statistics, like confidence intervals. And we're going to do a lot of exact results, and then we're going to say, but these cases were all set up to work out really nice. So what if we don't know the distribution of this or that? And then we're going to try to say things about large samples at least, because we sort of maybe know asymptotic distributions of things. Maybe that doesn't make any sense, but I promise you that there is a use for this coming up. If you're following along in the course notes, we're at the end of chapter 2, but there's one section which probably looks out of place, and that's because I just shoved it into the notes like the morning we started class this semester. And that is a section about the sample variance, because I just sort of have been sneaking that in. You know, I've been having you work problems on the sample variance, but we haven't really talked about it very much. And so I don't know, if you're looking at that section, I think it's going to seem very disjointed. I have to find a better place to put it. But I do want, so that we can use it going forward, to talk about a few more properties of sample variance that we haven't talked about yet. So check this out. Sample variance. I'm going to let x1, x2 out through xn be IID from a distribution with mean mu and variance sigma squared. So our sample variance we are taking in this class to be s squared, which is the sum of the xi minus x bar all squared over n minus 1, which is a little weird because we're trying to estimate a true variance, which is an expected value of x bar minus mu squared. And so we're trying to estimate that by changing out the the mean of the distribution for a sample mean, and so approximate this guy by taking all of our x's and subtracting our estimate for the mean, squaring it, and dividing by n. That looks more reasonable, more common sense, but we did show that if you take the expected value of this and run it through, you won't quite get sigma squared. So we had to change this n out for an n minus 1 to make this an unbiased estimator of sigma squared. Okay, so we already know, one, that this is always an unbiased estimator for sigma squared. And then two, from problem 24 on the review, we have an expression, and it's horrible to derive. I have made it a homework problem in past classes, but I didn't do it this time. And it is equal to the fourth central moment. So down here, I want to say mu4 prime is, that's not a derivative, but it's usual notation for when you have centered the moments. So a usual notation for like the expected value of x to the k is mu sub k. This is just a common notation for this. And mu sub k prime means you have centered it around the mean. But we'll talk about that later. This is just a definition. It's not a derivative. Okay, so we could show, it is horrible cranking out of horrible algebra, that this is mu4 prime minus n minus 3 over n minus 1 times sigma squared, which of course is sigma to the fourth, but I kind of like to write it like this in computations because I think of the variance as a thing, you know, that I'm operating on. So I kind of like to leave the variance alone rather than thinking of it as a standard deviation to the fourth over n. Okay, so from this, we can see that if this fourth central moment is finite, then it is easy to show that this variance goes to 0 as n goes to infinity, because this guy is going to 1. By the way, if the fourth central moment is finite, that implies that the fourth uncentered moment, the expected value of x to the fourth, is finite. And that implies that lower order moments, so the expected value of x squared, is finite. And so this will imply that we have a finite variance. But if this is finite, then we could show, if we were being more careful, I'm just going to claim it for now, that the variance of this guy, the limit is going to 0 as n goes to infinity. So I skipped a few things. One is showing this horrible expression, and the other is convincing you of what I was just trying to say about if centered moments are finite, then the non-centered versions are also finite, and vice versa, and lower order versions are finite. Point of all this is, we'll talk about this later after the exam, but the point of this is that to combine this and this to say that s squared is converging in probability to sigma squared. So this implies by that theorem that s squared, which has an n in it, but you're not seeing it in this notation, is converging in probability to sigma squared. It also implies that the biased version of s squared, so the sample variance that a lot of people like to use because it just feels weird to divide by that n minus 1. You're trying to compute an average squared deviation from the mean. So this is the other version of sample variance, and this is n minus 1 over n times our version. And this also has to go in probability to sigma squared, and that's by Slutsky's theorem, because we just kind of showed that this is going in probability to sigma squared, and this goes to 1. So it's a Slutsky's theorem result, which is another reason that a lot of people use this, because they say, well, in the limit, it's all the same. But I wouldn't use this for a small sample size. Okay, so the next thing, probably the last thing I can get in today, I think is super, super cool. And that is if we actually know the underlying distribution here, and we're going to look at the case of a normal distribution, I can tell you the exact distribution of s squared. So it doesn't have a name, but if I multiply and divide by a certain constant, it does have a name. And this, I think, is one of the coolest things that we're going to do today. It's nothing compared to the UMVU, but it's pretty darn cool. So now I want to suppose that x1, and we're going to need this all over the place for what's coming up, which is hypothesis testing and confidence intervals. So suppose that x1, x2 are IID, and now they're normal with mean mu and variance sigma squared, and assume that sigma squared is finite. I want to find the distribution of S squared. And on the current homework on problem 1, you, I think, are showing an algebraic relationship here. So by homework 5, number 1A, I believe, I could be wrong, I don't have the homework in front of me, you are showing that normal or not, well, normal in your problem, but it doesn't depend on normality, that you can write this guy, the sum of xi minus mu squared over sigma squared, equal to this guy, the sum as I goes from 1 to n of xi minus x bar squared over sigma squared, plus n times x bar minus mu squared over sigma squared. That's what a lot of the homework has been so far. It's been places for me to hide some of the computations that I didn't want to take class time for. So check this out. This guy in the middle, if it was divided by n minus 1, it would be s squared. In fact, this is n minus 1 times s squared over sigma squared. And I'm telling you that you already know the distributions of the other two terms. So let me call this A and C, and the middle one B, but I already wrote under it. So let's look at the distribution of A. I am going to rewrite this whole thing as I'm going to pull the 1 over sigma squared into the sum, and then I'm going to pull the square out of everything. So A is actually equal to the sum as I goes from 1 to n of xi minus mu over sigma squared. Just another way to write A. And starting with the assumption that these guys are normally distributed with mean mu and variance sigma squared, this thing inside the parentheses has a normal distribution with mean 0 and variance 1. And if you square a normal 0, 1, you get a chi-squared with 1 degree of freedom. So this whole thing with the squared is chi-squared 1, which was another homework problem. And if you add up a bunch of chi-squareds, I guess we haven't shown this yet. So if you add up a bunch of chi-squareds, you get another chi-squared with the degrees of freedom added up. And that is really easy to show using moment generating functions. So let me write this as the sum as I goes from 1 to n of wi. W's and v's are my favorites for chi-squareds. I don't know why. Where wi is chi-squared 1. So if I want to look at the moment generating function for A, this is a sum. So because things are IID, the moment generating function of this sum is the moment generating function for one of these guys raised to the nth power. And the chi-squared is a gamma 1, the chi-squared 1 is a gamma 1/2, 1/2. So if you go to your table and grab the gamma moment generating function, get that to the nth power. And this holds for t less than 1/2. And so if you raise that to the power and the other power, you get to multiply the exponent. So this is 1/2 over 1/2 minus t to the n over 2, which is the moment generating function for the gamma with parameter alpha equals n over 2 and beta equals 1/2, which happens to be how we defined a chi-squared n. So what we have just shown is if we add up n independent chi-squared 1s, we get a chi-squared n. And we could just have easily have shown that if we add up independent chi-squareds with different degrees of freedom, we'll still get a chi-squared, and the degrees of freedom of that will be the sum of all the individual degrees of freedom. So A, the term on the left-hand side of that expansion, is the sum of a bunch of chi-squared 1s. And so now we have, going back to this, we have the distribution of A. Right, so we know that A is chi-squared n. So any questions before I move on? I just love this because it's just like, it takes a piece of everything we've done since the first day of class. It's just like all coming together now. Okay, let's look at the distribution of C. So C is the square, sorry, not square root, it is n times x bar minus mu over sigma squared. And I can write this as x, I'm sorry, the x bar minus mu was also squared in this C. Scrolling, it's right here. Okay, so I can rewrite this as x bar minus mu over sigma over the square root of n squared. And because the thing inside, because x bar is normally distributed with mean mu and variance sigma squared over n, the thing inside without the square is normal 0, 1. So we're squaring a normal 0, 1, so we know that that has a chi-squared 1 distribution. Okay, so we have A equals like a B plus C, where B is n minus 1 s squared over sigma squared. And we have that this guy has a chi-squared n distribution, and this guy has a chi-squared 1 distribution. And I want to use this to try to find the distribution of this. Remember I said we could find the exact distribution of the sample variance, but it doesn't have a name, but it does if it has constants in front of it and under it. This distribution of the circled thing has a name. And so the next step is going to rely on another result of problem 1 on homework 5. So problem 1 on homework 5, you were showing that for the normal distribution, the sample variance s squared and the sample mean x bar are independent. Okay, so this guy, this B is again n minus 1 s squared over sigma squared. This C, that is not an arrow, that is not convergence. That is the same thing. And the C, here's a long squiggly equal sign, is n x bar minus mu squared over sigma squared. So check this out. This guy, the only random thing in there is the s squared. So this is a relatively simple function of s squared. This guy, the only thing random in there is x bar. So this is another relatively simple function of another random variable. So these two are independent from homework 5, problem 1. The entire problem, all the parts, are leading you to show that if you started with a sample from a normal distribution, that x bar is independent of s squared. That's the point of homework problem 1 on homework 5. So check this out. I've got A equals B plus C. I've got B and C independent. And so the moment generating function of A is equal to the moment generating function of B plus C. And by independence, if you need to, write this out, but it's kind of what we've been doing all along. This is the expected value of e to the TA. That's the expected value of e to the TB plus C. That is a product, e to the TB times e to the TC. By independence of B and C, this is the expected value of e to the TB. And you can break up the expectation by independence. This is the moment generating function of B, and this is the moment generating function of C. So I've got the moment generating function of A written as a product of the other moment generating functions. I know the moment generating function of A because it's a chi-squared. I know the moment generating function of C because it's a chi-squared. We're going to find this guy and then identify the distribution. So we've got the moment generating function for B is the moment generating function for A over the moment generating function for C. And A was a chi-squared n, so that was 1/2 over 1/2 minus t to the n over 2. And C was a chi-squared 1, so that's 1/2 over 1/2 minus t to the 1/2. And this is 1/2 over 1/2 minus t to the n over 2 minus 1 over 2, which is n minus 1 over 2. So it's looking like a gamma with parameter n minus 1 over 2, 1/2. It's looking like a chi-squared n minus 1. So this is the moment generating function for the chi-squared n minus 1 because it's a gamma n minus 1 over 2, comma 1/2. So because they uniquely determine the distribution, we've got that B is chi-squared n minus 1. We didn't have that A and C are independent, and so we had A equals B plus C, and we were trying to find the distribution of B, and it would not be helpful to say that B is A minus C, because if you took the moment generating function of B and you kind of translated this through, you would get like a moment generating function. You would not be able to break up the expected value here because A and C are not necessarily independent. And also, while it appears that we've shown, because we had A equals B plus C, and we had that this was chi-squared and this was chi-squared, and we then showed that this was chi-squared, we can't in general say that a chi-squared minus a chi-squared is another chi-squared. Just think about it. The chi-squareds take on values from 0 to infinity. And so if you just took two chi-squareds without a specific kind of relationship and subtracted them, you could potentially get negative numbers. So that doesn't even make sense for the chi-squared distribution. So we were a little bit tricky, but what we have is, so this is the important final result. So if we have x1 through xn IID normal mu sigma squared, this implies that n minus 1 s squared over sigma squared has a chi-squared n minus 1 distribution. I want to say super important, but I think I'm losing credibility because I'm saying everything is important. So who knows? This might come up again. So if you want to know the distribution of s squared, you know how to do it. It's a G inverse. You could actually find the PDF for s squared by saying like G of s squared, thinking of s squared as a symbol, is n minus 1 sigma squared s squared. Like I would call it T or something, so you didn't have that s squared. And you could actually do the G inverse stuff to find this PDF for s squared. It's not nice. It's not known, and it doesn't have a name, but it does have a distribution. But the nice known named one is not for s squared, but for s squared a little bit adjusted. So we're gonna start using chi-squareds even more, and I have like a minute, maybe less left. So let me just give you, I don't know if we wrote this down yet, but if we have a chi-squared n, that is a gamma n over 2, 1/2. And this tells me that the expected value of a chi-squared is alpha over beta for the gamma distribution. So is n. It's usually easier to remember that the expected value of a chi-squared is equal to the degrees of freedom of that chi-squared. And the variance, last thing, I think I'm running over here, this would be alpha over beta squared, so that would be n over 2 over 1/2 squared, just using properties of the gamma distribution, and this is 2n. And so from this, I'm totally out of time, but if you wanted to find if you wanted to find the variance of s squared for the normal distribution, you could say, well, I don't know about s squared, but I do know about n minus 1. I'll do this next time. Sigma squared, s squared, so like I could adjust it and pull constants out and use the fact that I know the variance of the chi-squared, and I'm rushing too much. So we'll pick up with that after the exam. So Wednesday is just going to be for review. Friday you'll have off. And on Monday, we are starting confidence intervals.